Hey, welcome. I'm just checking my stream, make sure that I'm actually recording some stuff, see what the audio sounds like. And let's see. It says we're recording, but we'll see what's going on. Stream settings, looks like we're good. Let me try. Somebody said my audio seemed a little low. How's that? How about this? Any better? Suppression. Just playing around a little bit. Sounds better. And mute myself so I can get back to. Cool. So on Friday, we missed Monday's class, but I'm back online. Just me this time. A little more boring, but we still get to have some fun. We still get to do some physics. And we're considering this planar pendulum, but adding the fact that it can bounce around on a spring. And the very first question that we were talking about on Friday was how many degrees of freedom are in this problem. And we figured out that this one has 2 degrees of freedom. And the reason that's important is that this is the number of independent measurements that we need to describe where this is. One way that we could describe it is say that if I call this my y-axis and this my x-axis, there's an x distance down, there's a y distance to the left and right. I know it's a little weird to put it that way, but I like to always have my angle be off the x-axis. So one way I could say is like, hey, there's an x and a y, and those are my 2 degrees of freedom. Another thing I could say is that there's a theta and a radius, that it can bounce up and down and it can move left and right. And this is really important because the number of degrees of freedom equals the number of equations of motion. What the heck's an equation of motion? Let's jump right into it. We'll figure out an equation of motion and then see what happens when we add this spring. So first step, let's just consider our 1 degree of freedom problem. So I have a pendulum, it's going to bounce back and forth. I need to know how is theta, like for this 1 degree of freedom. If I call this one theta, that's my degree of freedom, then we'll call this like L. What is its equation of motion? And the way I get that is I can look at the sum. Do I want to look at forces or moments? Let's just look at the free body diagram because that'll give us. So I have an mg and a tension, and all that is going to be equal to, if I'm using theta and r as my coordinates of like how do I describe where this is, r is always equal to L. So r is a constant, and I can say that this is my MAR, this is my MA theta, or if the pendulum is at an angle, MA theta is 90 degrees to that angle, MAR is parallel to that angle. And now if I just sum the forces along that A theta direction, I'm doing that because I already know how this all works out, but I can say MA theta equals negative mg sine theta. And that one's a little harder to see, but when I break this into components that are either parallel to the tension or 90 degrees to the tension, then some similar triangle magic tells me that that is the angle theta. And this A theta, when I'm in these polar coordinates like that, I can say that it's AR along this ER direction plus A theta along that E theta direction, or R double dot minus R theta dot squared along ER, and R theta double dot plus 2 R dot and theta dot along that E theta. Again, this might seem like a little bit of magic. It's not. There's some math, there's some solid math behind it, and if you ever do want to go through derivations, there are ways to derive it. Or if you never want to do the derivation in your life and you just want to say, like, give me the equation, you can always find, whether you Google it or you look it up in a textbook, there's always an equation of what is acceleration in a polar coordinate system, and it's always the same equation. It doesn't matter if it's a pendulum, if it's a pendulum on a spring, if you're in a roller coaster going around in a loop, or a carousel moving around in a circle and changing what horse you're on. If you're describing things with R and theta, this is always your acceleration. So you can always look it up, you can always derive it, but it's always going to be the same result. So because R is constant, like R equals L, then all these R dot terms disappear, and then I have ML theta double dot equals negative mg sine of theta. So theta double dot equals negative g over L times sine of theta. Now in the pendulum, I have 1 degree of freedom, so I have one equation. I'm going to write EOM, equation of motion, DOF, degree of freedom. One equation, 1 degree of freedom, 1 equation of motion. If I know how theta's acceleration relates to itself, then I can solve this problem. Like, I can integrate this and get theta as a function of theta dot, or I can integrate it and get theta as a function of time. But there's only one thing that I need to worry about. Now let's add that complicating factor, the fact that we have, let's start like this. Now I'm going to say that this is K times R minus L0. So there's some spring constant times that R minus L0. And that's just giving it, if it's K times R, then it would be the spring is unstretched when it's at the origin. L0 just gives it some unstretched length. I still have gravity acting the same way. And my acceleration does not change. I still have those 2 components of MAR and MA theta, but now I need to consider both of them because I need 2 equations of motion. I need 2 equations to describe what are my system's equations of motion, because I have 2 degrees of freedom. So I'm going to say my sum of the forces along that R direction are equal to that negative K R minus L0 plus mg cosine theta, and that's all equal to MAR. Sum of the forces along that theta direction are going to be, I don't have any spring constant there, so it's the same equation, negative mg sine theta equals ma theta. But now I don't have that simplification that R is always a constant value. R is now a changing value. So when I plug that in, I say m times R double dot minus R theta dot squared equals negative K R minus L0 plus mg cosine theta. and then m times r theta double dot plus 2. Nope, that 2 looks a little weird. R dot and theta dot equals negative mg sine theta. And now if I want, I can start simplifying things. So here's equation 1, equation 2. These are my equations of motion. So in terms of like getting to a point of like, are there equations? Can I identify them? I've identified 2 equations of motion, and they're independent from, well, they might not be completely independent, but they're 2 different ways of describing r and theta, and they are coupled with each other right now. I'll show you some engineering tricks in a second about how I can decouple these equations. But for now, the general kind of solution is that yes, this is a problem where the amount of swinging that I have, like the more that theta is changing, the more spring stretching I have, and the more spring stretching I have, it's going to change that how theta is affected. So it's, when you first look at it, it seems kind of complicated, but we can make some simplifying assumptions. So let's do that. Let's simplifying train, because we're engineers. So we drive the train as the engineer. Choo choo. Yeah. So the simplify train. First, let's start getting rid of the masses wherever we can. And so r double dot minus r theta dot squared equals negative k over m times r minus L0 plus g cosine theta, and then r theta double dot plus 2 r dot theta dot equals negative g sine theta. Okay, not simplified much yet, but I can start saying like, all right, theta is much less than 1. So if that's the case, so we'll say if, then sine theta is theta. I can say that it's approximately theta, but theta plus some higher order terms. Cosine theta, that one's just 1. Like if we're near 0, then the first order approximation for cosine is that it's equal to 1, that it's a constant. And theta dot is much less than 1, or that it's also much less than 1. And let's just keep it. So theta is much less than 1. Theta dot is also going to be much less than 1. That means theta dot squared is almost 0, because if something is like 0.01 and I square it, now it's 0.001, so it's even smaller than it was before. And let's see where we get with that, with those kind of things. So I start dropping things in. If I see a theta dot squared, that goes to 0. So r double dot minus 0 is negative k over m, r minus L0 plus g. So that g cosine is now just a g. That's pretty nice, because this is r double dot is only a function of r now. So I have a completely independent equation in that case. That's a good start. And then down below, I have r theta double dot plus 2 r dot and theta dot equals negative g times theta. And this part, I need to get rid of that r and that r dot somehow, because that's like a nonlinear coupling, at least if I want 2 independent equations, right? So up top I have an independent that this equation is describing like just a mass that's hanging and it's bouncing up and down. And then this equation is describing how it rocks back and forth. And so what I can do is say that R is usually, like, let's say that it's equal to L0 plus a small delta R. And delta R, we're going to say that it's something kind of small. So if that's the case, where delta R will go much less than 1, something like that. So if that's the case, then this value of R, we can say that it's L plus that delta R, the L0 plus delta R, or a magic arrow, theta double dot, and I'm going to just set it equal to for now, but G over L0 times theta, because this R dot is equal to just that delta R dot. So when it's a theta dot times that delta R dot, both of those are much less than 1, so both of them times each other are going to be much less than 1. So now I have simple pendulum equation, simple spring. I say simple. When I say simple, what I really mean is that it doesn't have like complicating nonlinear effects. Not that the problems are simple and you should immediately understand them. So we have this simple pendulum equation, a simple spring equation, based on these original like nonlinear equations of motion. So that's our like simplifying train. And I thought that would be a good place to talk about for today, of like, how do I get from degrees of freedom? I know how many degrees of freedom I have. How many equations of motion do I have? Okay, thanks so much for joining, and I will see you next time.